So, these are my financial disclosures. The depth of field, the aperture, spherical aberration, the new classification, and the new IOL models, these are the parts of my talk. The depth of field, I just want to start with knowledge from the photography. So, the objects, the closest and the furthest that you have and appear clear, that is the depth of field in photography. Similar is the depth of focus that we have in an optical system. Instead of object here, we have image, and we have all the different depths that we use, and we have all the different clear images that we have from the optical system. And these optical systems usually are depending a lot on the aperture, which is our pupil, or in photography, in different photographs. So the pupil diameter or aperture are very important to actually have better focus on different distances. But now we have to go on into the third term, which is the spherical aberration. Spherical aberration, why we know that spherical aberration is important for the depth of focus. We knew that for when we used to do LASIK surgery in hyperops, that somehow, if there has a hyperop of 45 years of age or 50 years of age, and we do the LASIK surgery on those, we improve the near and the distance and the intermediate vision simply by increasing the spherical aberration. Either both positive or negative can have an effect on the depth of focus. But unfortunately, when we do any kind of surgery or when we're living in a real life with the cornea doesn't have only spherical aberration, but a lot of other aberrations which may have an effect on the actual result, on the final result. Also, we have to consider that against this is the Stiles-Crawford effect. And this is an effect that you have with the amount of the macula which has a clear view. It is further, it is much clearer when it passes through the center of the pupil instead of the periphery. So Stiles-Crawford effect does limit the transparency of an optical system and also the depth of focus does. So ESCRS in the recent years tried to do a new classification in order to clear all these fantastic lenses and fantastic technologies that we have. And I will try to point that out for you quickly. The first cutoff is 2.3 diopters. So roughly is about 45 centimeters. The partial range of focus lenses, IOLs, are either the narrow range of focus up to 1.2 diopters, and this is the straightforward monofocal. Enhanced depth of focus, or the enhanced EDOF, or the enhanced monofocals, can go up to 150. And then whatever goes more than 150D, so whatever goes more than from 80 centimeters to 45, 50 centimeters is the extended range of focus lenses. I'm not talking about any different thing than the terminology used by the ESCRS. Go back to the full range of focus, and in this particular group, we are putting all the lenses who can give you more than 2.5 diopters of clear vision in the defocus curve. So clear vision from distance to up to 40 centimeters. Now, here we have the steep transition, what we used to call bifocals. So bifocals had one area which is very good for near, one for distance, and not so much in the mid. We have the smooth transition. In this category falls all the IOLs which have the trifocal kind of depth of focus. And the ideal is the smooth continuous range of focus, from distance to near, without any sort of wave into the depth of focus. And these are usually the focus curves that we have in all these categories. And so how can we know, how can we get this kind of knowledge and try to put it into our everyday practice? Let's presume that we have here a lens with a defocus monocular photopic as it is on the left-hand side. And we do a monovision of -1. So this is where we are aiming for pure emmetropia, defocus binocular, and if we have monovision of 1 diopter, this is how the binocular photopic is changing into a more even, smooth, continuous defocus curve. This is what we ideally can have if we do a little bit of monovision in EDOF spherical aberration lenses. But these patients don't have the stereo acuity for near. So if the patient in this category wants to do something like a very small near task, it cannot have the stereo acuity. So we're losing a part and we're gaining a part. So in other ways, you have to consider also what is the corneal wavefront, total aberration, in order to have the final result. In our study with a spherical aberration lens from Rayner Company, the EMV lens, we had 3 strategies. The emmetropia, the mini monovision up to half a diopter in one eye, the modest monovision up to 1 diopter in one eye, and the full monovision. And we wanted to see what is happening in each category, both monocular and bilocular. So once we do monovision up to half a diopter, we are increasing for near, we are losing a little bit for distance. If we go up to 0.1 diopter monovision, we are increasing more for near, losing for distance, and not much difference with the full monovision. If we try to do now everything as a binocular test, look, mini monovision, very good for distance, better for near, modest monovision up to 1 diopter in one eye, and you have a very nice continuous vision from distance to up to 3. So this is something very important to know. With these lenses, you don't need to do monovision more than 0.75 to have a continuous vision for all different distances. And this is what you have with binocularity. Near vision improves, distance remains the same. So if we want to put into different categories lenses that we know, enhanced and Ray-1 is in the enhanced, and Elon, VVT, and Vista are pure CR in the extended. And just to show you a new lens which is coming, Odyssey, which is supposed to be on the continuous, but if you see the depth of the focus curve of Odyssey is actually falling into the smooth transition. To summarize between EDOF and multifocals, as it's very well said, is the focal points are in one single, the other one are distinct, and also the near vision, which usually is not the case for the EDOF, but usually is working very nice with the trifocals. But you're losing something, and you're losing in a sense of halo. Why halo is happening? This is something that comes from physics, and it's very clear. Halo is happening when you have simultaneous vision IOLs. What it means is that when you have a trifocal lens in a patient, then you are creating 3 images, one for distance, one for intermediate, and one for near. All 3 images go back to the fovea. Now, the brain cannot select very clearly, but if the surrounding is highly illuminated, if the background is highly illuminating, then the defocused image is suppressed. That's why people with trifocal lenses don't have halos when there's bright illumination. In contrast, when it's dim illumination, where the background is dark, then the images of near and intermediate come in focus. And that's why you have the focused image appear and you have halos. So that is the reason that you have halos. So the more focuses that the lens has, 3, 4, 5, the more halos they will have. And this is rule of physics, simple as that. Positive dysphotopsia, another problem, has to do only with ESCRS design. So ESCRS design has some good things and bad things. This is the image which was drawn by an ophthalmologist, a consultant from UK. He's describing, he had one-eyed hybrid EDOF, one-eyed trifocal, and he's describing the way he's perceiving the light at night. This is with a trifocal, this is with a hybrid, and the image with both of them I just showed to you. Let's go back another step and see what we mean by halos and glare. These are different images, you know that, but there are halometers as well. So there was a very nice study done by Oliver Findle with a halometer which showed that EMV induces much less halo than all the other lenses, especially the lenses de Vivite. So we do know that there are lenses that can induce less problems than others. What about spiral? The spiral technology. The spiral technology comes with the archimedial shape. And these are some artistic designs of this shape. We used to have spiral technology in contact lenses, and this is an image of a contact lens which has near and distance in a spiral form and used to work very nice, but it was rather difficult to adapt for the intermediate ones. And we have the Fermat parabolic spiral, which is basically the distance as you go from the center to the periphery makes smaller and smaller, and that difference in the distance on the spiral creates the depth of focus, a little bit like the lens that we are going to discuss now. We had the first study, which published about a month ago with optimized A constant and a very high refractive accuracy. As you can see, both sphere and cylinder are very close to 0.